trionic array 2, we're given an integer array nums of length n. A trionic array is basically where we have a strictly increasing, strictly decreasing, and then strictly increasing. All continuous without any gaps. These are subarrays, and these have to be some length. They cannot be non-empty. They cannot be empty, so they have to be non-empty. We need to return the maximum sum of any subarray which is a trionic one in nums, right? So this is basically we need to understand the nature of increasing 1, decreasing, and increasing 2. So this is something that we need to analyze, we need to focus and draw conclusions, right? So here, what are the cases? Let's say the cases can be they are increasing, that is nums of I is less than nums of I plus 1, right? Or nums of I is equal to nums of I plus 1, or the last case will be decreasing, right? So if this is the case where they are equal, in that case it can be considered as a partition, right? Suppose if it's increasing then decreasing, but I got a 3 here. In this case, this entire thing is invalid now. So I can continue ahead without, considering anything before this, right? The next thing is if it's increasing or decreasing, right? If it's increasing, it can be an increasing 1 or an increasing 2, in the sense that it can be L to P or Q to R, right? It can be any of the thing. But if it's decreasing, there is no other choice but to consider it as the middle, right? So here, if it's decreasing, I get an advantage of not worrying about decreasing anymore, right? Because it's fixed, it's going to be the middle part, right? So decreasing is the foundation, right? Reason being it's fixed, leaving us with no choice. Right? The next thing, this point will lead to the increasing part and increasing 2 part. If we focus on increasing 1, right? And by the way, in the constraint, if we look at it, things can be negative, right? So this is going to get us to the second case where things are negative. Elements can be negative, right? Or actually I should write it, instead of a case I should write it as a conclusion, in the sense that it's a conclusion. It's not even a conclusion, actually it's just given, but still this is going to lead us towards something that is related to increasing 1, because now that we have fixed decreasing, right? We suppose we started with getting all the decreasing part, right? We went through the array, we got the decreasing part, which in this case will be this, right? Now if I have the decreasing part starting from P to Q, right? If this is decreasing, then I can expand backwards for getting the increasing one and forward for getting increasing two. If I expand backward, how much should I extend, right? That's the question. Firstly, expand or get all the decreasing sub arrays, expand back to get increasing one, to get increasing one, expand till it's valid, in the sense nums of I is uh, smaller than nums of I plus 1, and at least once. This needs to be done at least once, in the sense that this needs to be expanded at least one. Even if it is negative, it has to be at least one because it cannot be empty, right? So otherwise, uh, expand till things are positive, right? By this I mean nums of I that we are including. Actually, I should do it this way since we are going backwards. Nums of I minus 1 that we are trying to include should be positive. It should be positive. Now comes increasing 2. So let me copy this. So I need to expand forward to get increasing 2. I need to expand till it's valid. In this case, it's going to be j is less than j plus 1. It needs to be expanded at least once, whatever the case is. And we need to keep expanding. Why? Here, there is no such case as this. Keep expanding till I can. Be greedy, like we do in Cadine's algorithm. Things are negative, but I can still be hopeful and expect a very large value after getting some negative values, right? If I get -1, -6, -8, I still include all these because there can be 100 next, right? So if I need to include this, if I need to include 100, I have to get all the elements before that. So for that I need to be greedy. So as I expand, I keep on increasing or decreasing my answer in this case, but I keep on uh, updating my answer, right? I'm keeping on maximizing my answer at every step, right? So at every expansion, keep maximizing the answer, right? So that's it. Last point could be have answer, or try to keep this up. Probably we know that we need to have answer globally and keep maximizing it. Right. So the first thing is getting all the decreasing subarrays. By getting, I mean getting the start point, the end point, and the sum of the decreasing array subarray, right? So if we try to do a dry run of probably this example, I guess 0, -2, -1, -3, 0, 2, -1. Right. So if we have this and I am getting the decreasing subarray, decreasing subarrays will be this one, 0, 1, this will be start point, this will be end, and this will be total. This will be total in the sense that this is going to be -2, right? The next decreasing subarray will be this one, so it's going to be 2, it's going to be 3, and -4, right? So if this is the decreasing, uh, to be honest, yeah, this is going to be the decreasing subarray. Yeah, cool. So now what I need to do is go through all the decreasing subarrays one by one, have a start pointer, have a end pointer, expand backwards. By that I mean my start will be initially this point, my end will be this point, or actually this point, right? And I can do the exact same thing that we are doing here. I think things will start getting more sense as I code. Time complexity will be for every decreasing subarray we are doing this. It's going to be O of n, even if it looks like we have a 2D loop, one loop inside another. Actually, we are going to have one loop, and then inside that, two different loops for expanding backwards and forward. And I think things will start making sense as I code. So let's get the size in n. Let's get the decreasing subarray. Right, let me call this decreasing. And what are things that we are going to need here is going to be, it's going to be start, end, and total, right? So let's have a tuple because total can be long. So to accommodate for that, let's have a tuple of int, and long. Initially, let's have a sum, which is 0. I will have a start pointer initially -1. Let's get uh, all the decreasing subarray, right? So here I can start from the first point, because start from index 1, because I need at least two elements to consider it as decreasing. Right, so let's start with 1, and at this point we can check if nums of I minus 1 is greater than nums of I. That means this is decreasing. Here, if it is decreasing, I am going to include it in my sum. But what am I going to include it? Right, nums of I minus 1 or nums of I. So why not include nums of I here in this if condition, and in else condition I can get the last nums of I, right, that I see. So let's get the nums of I minus 1 here, and else at this point I can uh, get sum plus equal to nums of I minus 1, right? Why am I doing this? Well, if I'm here, right, I see that minus 2 is greater than minus 1, so start will stay negative 1. I see that or it will become negative 1, so I am going to reset it to negative n at this point, and sum is reset to 0, right? So at this point I have a answer to put in the decreasing vector, right? What is that answer? It's going to be decreasing dot emplace back start comma the end pointer is going to be I minus 1. I can consider I minus 1 as the point, and when I expand from this end point, then suppose this is the decreasing subarray. In this case, this will be the ith pointer where I am at. That's why I came into the else condition, and that's the reason I'm going to go for I minus 1, so that I can check the increasing part later on when I'm expanding for increasing 2, right? And that's the reason I want I minus 1 here. And this is just an implementation detail, by the way. And lastly, sum, right? So this is going to get me the decreasing answer or decreasing vector. But there is one thing that we need to take care. For example, if it's not decreasing and it came into else condition due to some other reason, suppose this was increasing, so I came here. In that case, I don't want anything inside I don't want these two lines to be executed, right? So I only want if it's already running, in the sense that it is decreasing and I have some subarray to use it and add it in the vector. So what I can do is check that if it's not equal to -1, that means it is running, and I can do these two statements, right? And the same thing goes here as well. So if start is equal to -1, that means uh, I mean the first time when I get a decreasing subarray, my start will be -1, right? I need to update it from the point when I get it. That means if start is equal to -1, I am going to update it. Otherwise, if things keep on decreasing, Suppose this was -1, -3, and then -4, right? In that case, I don't update the start point. I keep it because start is not equal to -1. It's already running. So this is going to give me the decreasing vector. Now I can expand increasing 1 and increasing 2. This is what I need to do now. For that, let me get the answer, which will be initially minimum. Things can be long, so my minimum value will be long minimum. I am going to go through all the decreasing subarrays, get the start pointer, end pointer, and sum. So the first thing is expand increasing 1 backward. That means I'm going to first I need to check if it's valid or not. First check if valid or not, right? By that I mean if there is something to expand, if there is space to expand backwards, that means this start pointer should have a start -1 within bound, right? Start -1 should be greater than equal to 0. That's the first validity. The next validity is nums of start -1 is something that needs to be increasing order, right? Nums of start. If this is true, then I have increasing 1. I have something, right? I can uh, expand backwards further, but I don't need to if I don't have to, right? So I have a increasing 1. Whatever it is, I don't have it. I mean, I don't have the value right now, but I know that I can at least have an increasing 1. So this decreasing is going to be usable if I have an increasing 2 as well, because I have increasing 1 already. So if this is the index that I am going to expand backwards, so I'm going to start with start -1. That means uh, this is the point which is going to be smaller than numbers of start, which it is already. So at least once, like we said in the conclusion part, uh, at least once I need to get the answer. So without getting into the loop, at least one I'll get the answer and I'll add it in sum, and that will be nums of I. Reason being I is at start -1, right? I have already included uh, sum of start, right? Sum of start is already included here. Start is I-1 and I have already included in the sum. I need to start including it from start -1, which is what I'm doing here. At least once it is included. Now I can expand further, and this expansion will be a while loop. I check if I is greater than 0. That means I have something to compare to backwards, right? It's like kind of doing the opposite thing of starting from I equal to 1, right? And things are valid or not. That is nums of I-1. This is valid because I is greater than 0. If this nums of I-1 is less than nums of I, that means it is increasing. And last thing is nums of I minus 1 is greater than 0. Why I'm doing this? I'm not going to be greedy here. Reason being, if this guy is negative, that means nums of I minus 2 will be further negative. Right? It's going to go down only because that's the case I'm handling. If I'm going backward, this is going to keep on decreasing. And if the first thing I'm getting as negative, then there is no point going backwards. That's why I keep it as positive and only go backwards if it is positive. So I'll do I minus minus. Before that, let me add this to my sum. Right. So now I have this guy. Exact same thing is needed for the other case as well. Let me copy this. Now comes the expand. Actually, let me copy the comments as well. Exact same thing is needed here, right? Let me copy this in this manner and paste it. My bad. Let me. Yep. So now I have copied the exact same thing, but I'm going to update it for increasing 2. I'm moving forward now. Check if it is valid or not. By this, I mean end plus 1 is less than n, right? That means I have something to compare to after end, and end at this point is I minus 1, right? So that means I have something to compare to further, and I'm going to check the validity. That means nums of end is less than nums of n plus 1, which is good within bounds because n plus 1 is less than n. This is going to be j because I have already used the ith pointer. So here end plus 1, because we are going forward, at least 1 it needs to be included, which we are doing by including nums of j. Lastly, I is greater than 0. Analogous to that should be j plus 1 is less than n, right? And this is going to be nums of j is less than nums of j plus 1. Lastly, in this part we are going to be greedy, so we are going to include it uh, regardless of the sign or the element value. I'm going to increment j here. Lastly, I am going to include nums of, we were including I minus 1 later on. I mean, in the first case, I'm going to include j plus 1 here. Why j plus 1? Because that's what we are including, because nums of j has already been included here, right? And nums of j plus 1 is what we need to include if things are ending at this point, right? That needs to be included here. So exact analogous things are here for this part, just that we need to keep on expand or maximizing our answer. So I'm going to maximize it here because things are valid here. I have already included at least once the increasing 2 part. I have already included this one at least once, and I already have decreasing. So I have all these 3 things, which makes it a trionic. So subarray is guaranteed to be trionic at this point, and this is going to be maximized here. suppose I don't enter this while loop, and that's the reason I am going to put the maximized part here as well, because if it is included at least once, that can also be my answer. And if I don't include the while loop and I don't have this, then I can potentially miss a case, and that's the reason I kept it here. Lastly, we are going to return the answer here, right? Let's see if this works. It does. Let's submit this. Time complexity will be O of n, because we are not really expanding or revisiting a point or element. We are only expanding it for like a sliding window, right? But the thing is, the space complexity can be reduced. Here we are using a decreasing vector, right? What I can do is not have this, right? uh, if I don't have this, right, and let's have index instead of I. Let's have index. Let me be careful here because I'm going to copy paste things. So this is going to be index, this is going to be index, this is going to be index. So now I can remove this part. We need an end here, so I already have a start and a index or sum. So start and sum is already something which is recognizable at this point, but let's have an end which is going to be index -1, and let me take this answer upwards, and let me take this entire thing and paste it here, right? I know things are going to be messy. Let me format it, right? So at this point, I think all things are good. Just that I need to, at this point, I can jump my index instead of just uh, updating it one by one. I can have a while loop which is going to go till the end of the array, right? So I can do index plus plus here, and I can actually jump further. This will work, I hope, but let's see. Okay, by the way, I don't need this. I should have not copied the entire loop, but only the body of the loop was needed. Let's see if this works. uh, I think this will also work if I submit this. Yeah, it does, just that it's a little bit extra time is what it's taking. Reason being, I can actually jump till j if I'm not mistaken, because we are basically getting all the increasing array, and only then a decreasing array can run, right, or can begin, and that's the reason we are jumping this. So I think the previous part was good enough. I don't know why this is still taking this long, but I guess this is the question. This was easier than the other hard questions that we see. So yeah, that's the fourth question. Thanks.